Welcome viewers. In this video we are going to continue our design of substation equipment foundation in Eurocode. This is stage 5 out of 7. In this we are going to do design of bottom slab for the equipment foundation. So as we know, these are the various stages involved in design of substation equipment foundation in Eurocode. Overview of calculation, foundation and soil parameter, load and load combination, stability check, foundation, bolt design. So these are the 4 stages we have already seen in our previous videos. Now in the 5th this series we are going to do design of a bottom slab. Followed by this there will be another 2 punching and 1 way shear for the bottom slab, and 7th is the design of pedestal. So after completing this single isolated foundations, we are going to do difference between the combined 2 pole and 3 pole foundation along with the isolated foundations. So let me look into that Excel calculation. You can see on the screen that the Excel calculation is which we are working on the design of equipment foundations. So now this is a design of bottom slab. So in this, first we need to find out the bending moment due to the upward pressure. For that, maximum net upward pressure for design we need to consider. So here we need to consider the ULS load case output, the bearing pressures which I already calculated during the stability check. So you can see on this tab that the bearing pressure for ultimate limit state we are having a 5 number of cases. So in order to design the bottom pad and pedestal, we need to calculate the maximum bearing pressure occurred in this among these 5 load cases. So that is 83.03. So that we are considering here. Downward pressure we need to deduct from the maximum net upward pressure due to the soil bearing capacity. So that you will get the net upward pressure. In order to calculate the downward pressure, we need to multiply the density of concrete and the density of soil according to the size of the soil and thickness of the raft. So here the GC is density of the concrete, that multiplied with the T is the thickness of the slab which we have considered in our second stage video. So that is 300, and capital D minus small d is the clear depth of soil above the bottom raft. So that we need to consider as a soil depth, that multiplied with the GS is the density of the soil which we already considered in our second stage of video. So that is 18 kilonewton per meter cube. So multiplying all this value, we are getting 29.1 kilonewton per meter square. That is GC, we know that it is 25, and 25 multiplied by 300 is the depth of or thickness of the raft we have considered, and 18 is soil weight, that we need to multiply it with the depth we have assumed as 1.5 meter minus T is 0.3, it is 1.2 meter. So multiplying this with 1.2 meter, so we are getting 29.1. Then net upward pressure is nothing but directing the upward pressure to the downward pressure which is formed due to the soil and bottom slab. Now we need to calculate the maximum overhang distance. So this overhang distance is nothing but it is the clear distance of bottom slab from the center of the foundation. So this is a overhang distance. We can consider L1 or B1 because it is a square footing. So both will have the same. So this L1 is nothing but L, which is a capital L, is a total length of the foundation divided by small l, the whole divided by 2. So this is a equation to find out the overhang distance. So we know already that foundation size is 1.6 meter and pedestal size is 0.7 meter. So the whole value is 0.45. So this is what we have considered here. As it is a square, both L1 and B1, that is both the length and width directions, the L1 and B1 are remain same as a 0.45 meter. Next, coming to the moment of slab. So we are calling this as a sag moment. Why it is? Because while we are applying this, suppose if this is subjected to the upward pressure, the entire slab will be subjected to that, then the bending moment will occur due to the upward pressure is in this direction. So this will form a sag moment because of the vertical column which is placed over the bottom slab. As there is a slab here, then this bending moment will like this. So this we are calling as a sag shape. So that is why we are call it is this as a sag bending moment. So this bending moment, we are, as it is a cantilever one, we are going to consider only the equations for the cantilever bending moment subjected to uniform distributed load. So here the dnu is the net pressure into L1 is a 0.45, so L1 square by 2. Actually this should be dnu1. So similar like in both the directions, as the upward pressure also remains same and the L1 L2 B1 also remains same, then the moment on both the side will be same. Now we need to calculate the reinforcement for the bottom pad. So for that we need to check EN 1992 part 1 section 1 also. So this is a design of concrete structures part 1-1 general rules and rules for buildings. So this is a code we need to consider while calculating the reinforcement for bottom pad. So first one is a compressive strength of concrete, that is characteristic strength we are going to consider as per our second stage video, where we have considered this material as grade of concrete is C25/30. Here that 25 is a characteristic strength of concrete under a cylindrical compression test, which is a 25 megapascal, and here that 30 is nothing but it is a concrete strength under a cube stress. Considering the cylinder and the cube sample, this stress value is find out from the test, so that this grade is called as C25/300, sorry, C25/30. And this is a grade of steel we have assumed B500B, which is as per the British standard BS 4449, which is having a yield strength of 500. So here this 25 megapascal is a cylindrical compressive strength of the concrete grade which we have assumed, and the design yield of strength we need to divide this 500 with gamma s. So gamma s we can find out in table 2.19 of EN 1992 part 1. So for that we need to refer page 26. So here this table you can see that gamma s of reinforcement under persistent and transient cases, that is general cases, 1.15 is considered here for normal reinforcement steel. So that is what we have considered here, 1.15. So 500 divided by 1.15 is 434 megapascal. Effective thickness of bottom pad we are deducting just 50 mm in the 300 mm of thick slab, so we are getting T effective as 0.25 meter. Then minimum reinforcement, for that we need to calculate the mean value of axial tensile strength of concrete. So for that the formula is 0.3 into FCK power 2/3. So for that we need to refer table 3.1 of EN, which is page number 31. So you can see this table 3.1 here, that FCTM value is given as 0.3 FCK power 2 by 3 for concrete grade of less than or equal to C50 to C50 bar 60. Other cases we need to go for 2.12 into log n 1 plus FC. So this equation is given here, or else you can directly consider this value instead of that, but we have considered like as we are doing with the drop down list for selecting the various grade here in the introduction page. So we can better use the formula instead of direct value, so that any grade if we are changing here in the introduction part or the material selections, then automatically this will calculate based upon the 0.3 FCK power 2/3 equation. So we are having 2.56 megapascal for the grade of concrete C25 bar 30, and as per class 9.3.1 of EN 1992, if you refer, that is page number 160. So here that for solid slabs under flexural reinforcement, it is mentioned for the minimum and maximum steel percentage in the main directions we need to refer 9.2.1 and 1 notes. So we can just move on to up to find out the class which is mentioned in that. So 9.2.1.1, which is showing AS minimum as 0.26 FCTM divided by FYK BTD. So BT we can consider as 1 meter of the bottom pad slab, and D is the effective depth or effective thickness of the slab, which is 250 mm, and this formula should not even less than the 0.013 BTD. So this is what we have mentioned here in our equation. So here that FYK is nothing but this FID, and FCTM we already calculated as 2.56 megapascal, and BT we are going to consider 1 meter of the strip, and the T effective we already calculated this as 250 mm or 0.25 meter. So applying these values to these equations, AS minimum is 383.42 square mm, and also it is stated that it should not less than 0.0013 BTT. So considering this, for 1 meter strip it is 325 square mm. So we are considering this 383.42 as the minimum reinforcement, and for maximum reinforcement it is mentioned in the same class. You can see here under the note 3, the value of AS maximum shall be considered as 0.04 AC. So that is what considered here by multiplying the PT equal to 1 meter, that is 1000 mm, with 0.04 with the effective thickness of slab 250 mm, that is 0.25 into 1000, it is coming 10,000 square mm. In any case this reinforcement should not go beyond this. If it is going beyond that, means we need to increase the thickness of the slab. Calculate the actual reinforcement required for the sagging movement in both Y and X directions. So for that, this is the equations which we need to follow, where B we need to consider a 1 meter strip to calculate the reinforcement, and K is nothing but the neutral axis depth factor. So what it means is suppose the Our slab is like this, having a depth, effective depth of TEFF. So then due to the tension at the bottom, the bottom fiber will tends to go in taking a high tension value, whereas in the top it will take only the compression, so that there will be a lever arm distance used to follow, that is Z. So this lever arm distance we need to find out. In no case this lever arm distance should not go beyond the 90% of the total effective thickness. So that is what this equation is formed. So here K equal to MSY is a moment, and B we are going to consider as a 1 meter strip, and T effective is we already calculated as it is 250 mm. So here you can see that, and FCK is a concrete cylindrical strength, characteristic strength, which is a 25 megapascal. And applying all this value in K, which is a neutral axis depth factor 0.010. So it means this lever arm distance is going to act nearby the tension zone, and we know that Z value is T effective divided by 2 into 1 plus the square root of 1 minus 3.53 K. So applying all this value, we are getting 225. So this 225 is nothing but 90% of 250 mm. So this is what we are getting. But if you are calculating this equation, T effective is 250 mm divided by 2 into multiplied by 1 plus square root of 1 minus 3.53 times 0.01, that is K, means it is coming around 247.77 mm, which should not be the right, because we are already knowing that the effective depth of the slab is 250 mm. Only nearly 2.3 mm is difference compared to that. So this value will not be the correct. So only the 225, that is 225, 90% of the T effective we need to consider. So in order to find out the effective lever arm distance, we need to check with the European code what it is telling, what could be the lever arm distance should be considered. So here you can see that members requiring design shear reinforcement for 6.2.3 class, it is mentioned that lever arm in no case it should not exceed 0.9 D. D is a depth of the effective depth of the member. So we have considered as this same concept here in our Excel sheet also, or else we can directly consider 0.9 effective thickness of the slab, so which is 225. So now the reinforcement, the tensile reinforcement can be calculated as mu divided by fyk into z. So don't get confused that z is not a section modulus of the slab, it is a lever arm distance as here it is explained. So applying these values, z value is 225 mm, fyk is 434, and the moment we are getting 5.471 kilonewton meter. Of course we need to convert this into Newton millimeter by multiplying 10 to the power of 6 here. which is divided by Fyk is 434 megapascal, and also divided with the Z value, that is lever-arm distance. And here that equation is applied by considering the minimum reinforcement, which is considered here as 323. So if you want to know that how much will be the value if without considering the minimum reinforcement, so it is coming only 56 square mm, which is very less for the moment. So we can consider this minimum reinforcement 383 square mm. By providing 10 diameter of 200 center to center distance, we are getting actual reinforcement as 393 square mm, which is greater than the required reinforcement. So we can consider 10 mm diameter at 200 center to center distance for the bottom slab in y directions. Similarly, we need to check with the moment for other direction, that is x directions. Anyway, that moment value remains same, 5.461 kilonewton. All input which are related to the x direction also same as y directions. So the value is coming here also the same value, 383 for the area of reinforcement. So again here also we are providing the 10 at 200 center to center distance. Coming to the top reinforcement for both the directions, as there is no top reinforcement required for this one, because as per the bending moment calculations we see only the sag reinforcement. That means only at the bottom of the slab is subjected to the tension, so we are providing here. However, in order to have a balanced reinforcement, we can provide some 50% of the minimum reinforcement, that which we have calculated here 383 square mm. We can consider 50% on both the side top reinforcement as 192 square mm. So by providing 10 diameter at 300 center to center distance, we are having 262 square mm as actual reinforcement area, which is higher than the required, that is 50% of tensile reinforcement, minimum tensile reinforcement 162. Then we can provide both the direction top reinforcement as 10 mm at spacing of 200 center to center distance, or else we can consider the same as for the bottom reinforcement. So this is all about design of bottom slab. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.